So good afternoon, everyone. Questions? Anything about the homework?
So on the extra credit problem number 9, you said that hand-wavy proofs will not be accepted, but you didn't say that specifically for problem number 4, I believe.
Okay, that dictate is applicable to the whole homework and to every problem you'll ever face in this course. So point is that just asserting something as a solution is not an acceptable thing, I guess. So I'm kind of stating the obvious, but in particular for that problem, I kind of highlighted that. I think it was for the XOR problem. I think I said that, yeah, because there are some unjustified intuition based stuff that one could say, or like take the example, um, like I think on Piazza I highlighted, like, right, I mean, if I just give you a bunch of AND gates, infinite supply of AND gates, and you can, yeah, it's intuitively obvious that NOT gate cannot be implemented using it, you might say so, but that doesn't constitute a proof. So I'm basically saying whatever you are claiming, kind of give me at least a logical sequence of reasoning which kind of justify your claim. Basically. That's
But for problem 4, I don't know if you addressed this on Piazza, but is it okay to work from the given fact that NAND is a universal?
Yeah, NAND being universal is something we have seen in the class, so that's fine.
Okay.
Actually, why is that true? When did I say that NAND was universal? When did I prove it? Anyone? What aspect of that I have stuff that I have taught results in us saying that NAND gate is universal? Huh? The normal form. Okay, remember the distinctive normal form is and followed by OR, and I had shown in the class that how by putting the bubbles in between I can convert it into NAND and NAND, and so I can always make it into sort of k input NAND gate for arbitrary k, and then you can show that I can implement a k input NAND gate using 2 input NAND gate. So NAND 2 is universal based upon what we have discussed. So anyway, that.
How would you show that you can't make an inverter out of just continuous?
So look at Piazza. I worked out the proof there on how you can show that NOT can be implemented using AND. Okay. Of course, the problem in the homework is different. It says I have and OR, okay? But I kind of gave you the style of proof that one could follow, and I think you should be able to kind of adapt that. Yeah.
There's a problem that says, give an example of a truth table.
The 3 billion, 5 billion, that one, right? Yeah.
A real example?
I don't know. Every function is real, right? Truth table is nothing but a description of a mathematical function. So I'm asking for give me a mathematical function which has that property. Oh, so I guess by real you mean is it? Can you point me to some practical system where it is being used? No, it's just give me a mathematical function with those properties. Yeah. Any other question? Okay. One other thing which kind of those of you approached me about the extra credit problems are the ones where it's perfectly fine if you want to do Google research and all. If there's some paper you encounter or some article you encounter or whatever, just cite it in your homework. I think that's fine. I mean those two problems are not easy. So just wanted to mention that. So if you are, I mean, it's conceivable that you can. I think problem 8 is something which, if you think a lot, you should be able to do it on your own. Problem 9 is tricky. Okay, so but I think I've received at least one solution for problem 9 thus far. Any other question before I move on? Okay, so the plan is I'm going to do a very quick recap of the 3 concepts I introduced in the previous lecture, which was one of those makeup lectures, and I trust all of you followed my instructions and have followed and watched the video. Unfortunately, YouTube doesn't say that most of you did. So, but I will in order to not encourage not watching those. I still want you to watch those, so it's going to be a very rapid review out here, and just to transition things over. Okay, so we had moved from kind of making arbitrary mathematical functions using Karnaugh maps or these kind of techniques to one where we said, look, let's create some useful building blocks, and then we can make more complicated stuff out of these building blocks. And last time around, I've introduced 3 of the 5 building blocks that were of interest out here. Which is decoder, encoder, multiplexer, and there are 2 more which are arbiter and comparator. Okay, but let's go over it. So decoder, what a decoder does is it takes as an input an n-bit number, where you can think of this n-bit number representing a decimal value. Okay, so like for example, if n equal to 3, then the value represented on these 3 bits would go from 0 through 7. Okay, so it basically represents, I can interpret this n-bit number as a positive decimal number. Okay, 0, 1, 2, 3 to the through 2 to the power n minus 1. Okay, at the output, I have m bits, m wires coming out. M could be as much as 2 to the power n. So the idea is that the input takes value 0, 1, 2, 3. So in my 3-bit example, 0, 1, 2, 3, 4, 5, 6, 7. On the output, I have 8 wires. Let's call them wire number 0, wire number 1, wire number 2 through wire number 7. And the idea is that if the input corresponds to the number I, then at the output, the ith wire will have a 1 in it, and all the other wires will have 0. Okay, so it's basically on the output at any given point in time, 1 and exactly 1 wire would be high, and this is what we had seen in the very first lecture, this concept of one hot coding. That is, I'm trying to represent something, some information, and depending upon how many distinct values that information can take, I have that many wires. And then if the value is the first value, the first wire is high. If the value is the second value, the second wire is high, and so on and so forth. So that's what's saying out here, that if whenever a is equal to I, that is the number represented by the n bits on the input, if it is high, if it is I, then the ith wire, bi, is the one which we raise. M could be less than, some of the output wires may be missing, so that's why we have m less than equal to 2 to the power n, but more generally m would be equal to 2 to the power n. And just to make the point that this can be interpreted in a somewhat different way also was that this operator less than sign, which is present in all programming languages and represents shift by a certain number of bits. So whenever we say x less than y, it says that think of x as a binary number and then left shift that number by y bits. So in particular, what we are saying is think of the binary number 1, which is basically 0, 0, 0, 0, 1, shift it left by a. So if a is 0, I continue to get 1. If a is 1, then I shift left by 1 bit. So previously I had 1 bit in the rightmost location. Now it will move left, and I'll put a 0 in the rightmost position. So I will end up with 0, 0, 0, 0, 1, 0, which is the number 2. If I so I shift it that many times. Okay, so essentially, if a has the value I, then I'm shifting it I times, which basically means that B would the ith wire on B will take the value I. If you kind of think about it, what's happening out here, that if A is 0, then B would be all zeros and 1, which means B0 is high. If A is 1, then B1 would be high. If A is 2, then B2 will be high, and so on and so forth. So that's what a decoder does. It's just a definition of a decoder. And I had shown that you can work out the truth table, and you can create implementation of this using our standard sort of approach that we have seen in the previous module. So in this particular case, I have 4 outputs, and therefore you kind of so it's what we really have out here is really 4 truth tables, one for B3, one for B2, one for B1, one for B0. And what you see out there is the realization of that. And the other thing you would see is that, like if you look at B0, B0 corresponds to a truth table where exactly one minterm is high. All the other minterms are missing. Likewise, B1 corresponds to the truth table where minterm number 1 is true. All the other minterms are false. And B2 corresponds to minterm number 2, and finally B3 corresponds to minterm number 3. So what you see out on the right-hand side is really we are systematically creating each one of those minterms. So we take A1, A0, we make them go through inverter, and then we create all 4 possible combinations that can, all 4 possible minterms that can be formed, and they map to B0 through B3. So that's a one-to-one implementation that I had shown. And kind of the harder part, which wanted to go over, was that we could, let me jump a bunch of slides here. Okay, yeah. The key thing was that many a times we want to create bigger decoder, meaning decoders which take more inputs out of smaller decoders, namely decoders which have fewer inputs. And I had given an example that, let's say I want to make a 6 to 64 decoder out of 2 to 4 decoders. So I'm giving you some decoders which have 2 inputs, 4 outputs, and I want to create a bigger decoder which has 6 inputs and 64 outputs, 2 to the power 6. And kind of the idea out here is the following, that 6 bits could be viewed as 3 pairs of 2 bits. I'm going to decode each one of them separately, each one of these pairs separately using a 2 to 4 decoder. And then I'm going to create my desired output for the big decoder by combining these things in different ways. So if you look at the lower 2 bits, A01, A being my input, then it can take 4 distinct values. If I look at A23, A2 and A3, they can take 4 different values. And finally, A5, A4 and A5 can take another 4 values, 4 distinct values. So the total combination can take 4 times 4 times 4, namely 64 distinct cases, which is what we want. And this is kind of shown out here also in this diagram. So on the leftmost table, we have A4 and A5 as the input, and Z0 through Z3 being the output. So Z0, Z1, Z2, Z3 are telling me what values A4 and A5 are taking. Like, so Z0 is high whenever A4 and A5 are 0, 0. Likewise, the middle table is telling me what values A2 and A3 are taking. And that I indicate by these 4 wires, Y0 through Y3. And then finally, the rightmost table is telling me what values A0 and A1 are taking. And now, let's say my 6 to 64 decoder receives the input 0, 0, 0, 0, 0, 0. That's another way of saying is that Z0 is high, and Y0 is high, and X0 is high. Right? Because they correspond to that particular combination. Or for example, let's say my input was 1 0 0 1 0 1. Okay, so if the 6 bits of A were 1 0 0 1 0 1, then I'll look out here and I'll say A5 A4 are 1 0. So that means Z2 should be high. A3 A2 is 0 1. That means Y1 should be high. And then A1, A0 are also 0, 1. That means X1 should be high. And therefore, in this particular case, if I want to signal the appropriate output high, that would correspond to Z2 and Y1 and X1, and so on and so forth. So there are 4 signals here, 4 signals here, 4 signals there. We form all 64 possible combinations of those, and that would give me the 64 outputs of my 6 to 64 decoder. Is this point not clear to anyone? Okay. So using this strategy, we can this diagram is just doing that. So I am taking my 6 bits, I'm splitting them into groups of 2 bits, 3 groups of 2 bits, each one of them I decode, and then I create all possible 64 combinations, and they will correspond to the wires B0 through B63, my 64 wires, that 64 outputs that I need. So I can make bigger decoders out of smaller decoders by kind of decoding groups of some groups of input bits and then kind of combining the results like that. I'd also talked about that. Why might we want to do it? Yeah, go ahead.
If you go back a couple things, are there more elegant ways to essentially what I mean? This essentially is it's brute forcing all of the total combinations to produce all 64. Is there a more elegant way to do that?
Unfortunately, not, because each one of them is depending upon only one minterm. So there's not any combination that you can do, right? Because I'm basically generating all the 64 minterms that are needed out here. Okay. Now, what you could do is, if I were to tell you that, hey, don't use these AND gates, you're allowed simpler gates and all, right? Like 2 input gates and all. Then it's possible you can begin to share some stuff across these things. Okay, but not the way I've drawn it out here. These vectors, yeah. And why might we want to do it? Well, the reason basically is that if we count how many gates, if I could have implemented the 6:64 decoder using my original Karnaugh map-based approach, in which case you would have seen that it would have required 64 6-input AND gates and also a bunch of inverters, in particular 6 inverters. So that would have a total of 390 gate inputs, so the cost would be proportional to 390. With the approach that we outlined just now, this one, you can count, and there are 12 2-input AND gates, 64 3-input AND gates, and there are also certain number of NOT gates, and you kind of combine all of these things together, the cost is lower. So it's more efficient area-wise, this kind of approach of using smaller decoders and then combining them. The problem with them was, anyone remember still from that lecture if you were there? So we are saving area. Where are we losing? Delay, time. It goes through more stages of gates. Okay, so it's a slower design. So it's always very common in digital design that things which are lower in area are going to be slower than something which takes higher area. So area and speed is a very common trade-off that happens, or area in this case being number of gates. Okay, so that was a quick recap of decoders. Decoders are useful because I can use them to implement arbitrary logic functions, because what a decoder is doing is giving you a signal for each possible minterm. And we have seen previously that a function is nothing but an ORing of some of the minterms. So if I give you a decoder, then I can construct any function by just picking the right minterms and then ORing them. In fact, using the same decoder and a bunch of different OR gates, I can create a bunch of different functions. Okay, so that's kind of a useful, useful aspect of decoders. Encoder is, as the name implies, inverse of the decoder. So again, this we had discussed last time, but just to provide you a quick recap. So let me, okay. So so decoder was going from binary to 1-hot. Encoder does the reverse. It goes from 1-hot to binary. So, and the truth table is exactly the opposite. So in this particular case, in this particular truth table, this is the input and this is the output. And it's basically saying that if A0 is high and the other A1 through A3 is low, then the output should be 0, 0. If A1 is high and the other 3 bits are 0, output is 0, 1, and so on and so forth. So input side is 1-hot, output side is binary. And as sort of we have seen before also, input is 1-hot coded, so there are a lot of input combinations which are not valid 1-hot code. Like for example, 0, 0, 0, 0 is not valid. Likewise, 1, 1, 0, 0 is not a valid 1-hot code, so they do not appear out here, and they are therefore don't cares. Looking at this, the encoder is kind of relatively trivial. If you look at like B0, B0 is high whenever A1 is high or A3 is high. So that's what you see. B0 is nothing but an OR gate, and likewise B1 is high when A2 and A3 are high. So that's what you see out here, and then yeah, that's it. And A0 actually doesn't affect anything. So the encoder implementation in this case, this is a 4:2 encoder, is straightforward, and in fact pretty cheap relative to the decoder. We had the same issue. We could design larger encoders from smaller encoders. And this was a trickier example, so I want to go through it in a little bit more depth. So what we have out here is I want to design a 16:4 encoder. So I'm getting in 16 bits of A, so they go from A0 through A15. And I want to encode it into 4 bits. So I need 4 bits of output, B0 through B3. So, and remember, A has to be one-hot coded. So one and exactly one of these 16 bits are going to be high. If they're not, then it's not a valid input. And again, kind of what we do is we first encode groups of 4, and then we combine them to get our final output there. So what we do is we feed A0 to A3 to encoder at the bottom, A4 through 7 to the second encoder from the bottom, A8 through A11 on the third encoder from the bottom, and A12 to A15 to the fourth encoder at the bottom. Now, and remember, each one of these encoder is a 4:2 encoder, so it has 4 wires coming in, and each encoder expects a one-hot code. But that's not possible because my 16-bit input is a one-hot code. Exactly one of these 16 wires will have a high value. That means 3 of these encoders are going to see 0, 0, 0, 0. Is that clear to everyone, right? I mean, since only one of these 16 wires is high and the rest are 0, that means only one of these encoders will see a one-hot code and the other 3 are going to see 0, 0, 0, 0. So somehow we need to be aware of this and keep track of that. So now when we are going to merge these things, I need that information. I need that information as to which encoder saw the 1. And we also need to know within that encoder, which wire saw the 1. Well, these are now these enhanced encoders, as I was calling them last time. They have 2 kind of wires coming out. Blue wire, which are 2 bits, and there is new red wire, which was not there in the previous slide. The red wire says, was the input valid? And the blue wire, its property is that if the input was not valid, the blue wire would be 0, 0. And if the input was valid one-hot, that is, it was a one-hot code, then the blue wire will take the appropriate value. So which means that if the 4-bit input was 0, 0, 0, 1, let's say like any one of these, so if the 4-bit input was 0, 0, 0, 1, then the blue wire would have the value 0, 0. If the 4-bit input was 0, 0, 1, 0, then the blue wire will have the value 0, 1. If the 4-bit input was 0, 1, 0, 0 as shown out here, blue wire would have the value 1, 0. And then finally, if the 4-bit input was 1, 0, 0, 0, then the 4-bit value out here would be 1, 1. If by contrast, the input was all zeros, which can happen in our example now because of the way we have split things up, then blue wire will have the value 0, 0. Red wire will have the value 0 if the input is invalid, if the input is all 0. Whereas the red wire will have the value 1 as shown for this third from bottom encoder, because third from bottom encoder is seeing 0, 1, 0, 0. So we see on the blue wire 1, 0, on the red wire we see a 1 out there. So red wire is basically saying, hey, this encoder is seeing a valid one-hot code, and blue wire is saying, and which wire within that encoder was seeing a 1. Now the claim now is that this gives me enough information to generate the 4 bits of B that we want. So if you think about it now, the red wire is telling me which group of 2 bits, which group of 4 bits the 1 was occurring in. And if you kind of look out here, the upper 2 encoders, the upper two bits of B tell me which encoder I'm going to. So if you think about it, A0 through A3, the output value on the B will always be 0, 0, and then some value, right? Because this is going from 0 through 3. So the output values can be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So the upper two bits of B will be 0, 0 whenever A0 through A3, one of them was high. If A4 through A7, if one of those bits was high, what would be the upper two bits of BB? Zero, 1, right? Because A4 is 0, 1, 0, 0, A7 is 0, 1, 1, 1, and the other two values are in the middle. Whenever A11 through A8 are one of them is high, then the upper two bits of my output will be 1, 0. And then finally, whenever the uppermost encoder is seeing the one hot code, the 1 in the one hot code, then the upper two bits would be 1, 1. So red wire state tells me the upper two bits of B. And the blue wire state of the encoder which is seeing a valid one hot code gives me the lower two bits. So in this particular example where A10 is high, I want the output to be, well, 10 is 1, 0, 1, 0. So as kind of already drawn from last time, the upper two bits have to be 1, 0, lower two bits have to be 1, 0 also. So we are seeing in this example, the lower two bits are appearing on this blue line out here for the third encoder. And we are seeing that this is saying that the third encoder is valid. The third encoder from the bottom is seeing a valid input. We take the 4 red wires and now we further encode it because one of those red wires is going to be high, the other 3 are going to be low. And so we have another encoding problem. We take these 4 bits and we encode them into 2, so we need another 4:2 encoder, and that gives us the upper 2 bits. Lower 2 bits, 3 of them will be 0, 0. 3 of the blue wires will see a 0, 0, and one of them will see either 0, 0 or 0, 1 or 1, 0 or 1, 1. And we want the state of that blue wire to appear on B0, B1. And to make that happen, we make use of 2 4-input OR gates. And I had talked about last time that how there is this notation that we are using, and this was that instead of drawing 2 4-input OR gates, and so essentially one OR gate operating on bit number 1 and one OR gate operating on bit number 0, we kind of use this notation out here where you see this OR gate, each one of the wire is a 2-bit wire, and the output is 2-bit. And what this says is that I take from each pair, I take the lower bit, feed it into an OR gate, and I get the lower bit of the output. And from each one of the blue wires, I take the upper bit, feed it into another OR gate, and I get the upper bit of the output. So it's literally kind of 2 OR gates in parallel, one operating on lower bits and the other operating on the upper bit. And this concept can be applied to any number of bits. LogicSim also supports it. It's often referred to as bit slice. I slice up my n-bit design into n 1-bit design, and so what we really have out here are 2 OR gates of 4 input each. Okay, this is not an 8-input OR gate. That's the very important point. There are 2 4-input OR gates out here. So we can combine encoders into kind of these larger and ever larger encoders. Question?
So if we're looking at a design, an encoder and a decoder aren't like labeled that based on their exact implementation, because this is like 4 to 2 encoder, but it has 3 outputs. It's just the implementation that lets us call it an encoder.
And actually, the reason we have this red output is because to cascade or kind of to gang together these encoder, I need this extra information. Okay, in Logisim also there is a this thing, and there's a similar wire. The other point I would like to make is that sometimes you would see that these decoders and encoders may have some other extra inputs also. Okay, like for example, it's not very uncommon to find decoders or encoders which may have an enable input also. And whenever enable is low, output is all 0 or something like that. Okay, so again, Logisim has kind of same thing, same story. So what I've shown you are kind of the most basic pure forms of encoder and decoder set there are. Any other questions on this before I would urge you to, if you haven't watched the recording of the lecture from last week, just because I go into this material in a lot more depth out there. For this enhanced 4:2 encoder, it has 3 outputs as we just discussed. So we have B0, B1, but we also have that red wire, which we can call as a valid signal, and you can kind of label it the values it takes also. So what you see out here is this valid signal. It is taking 1. It's 1 whenever the input is a 1 hot code. Whenever input is 0, 0, 0, 0, this valid signal would be 0. And other values, other non-1 hot code values should never occur. Okay, that's in a system. So they, in a way, should be don't care. The final module we had discussed last in that lecture was the multiplexer. And multiplexer corresponds to this function that we encounter in many devices, which is many sources of information, but the destination is interested in only one of them. So like many memories, memory banks, and the CPU, the processor in your computer, wants to get the data from one of them. Okay, so it basically tells some traffic cop in the middle saying, I need data from memory bank number 0 or memory bank number 1 or 2 or 3 or whatever. So I have a bunch of sources. I have this traffic cop, which is going to let information from one of the source go to the output. That's kind of the concept. So the multiplexer in this particular case has n sources, A0 through AN minus 1. Each source is k bit each. So like for example, k is the size of the data. So like when we say it's a 32-bit processor or a 64-bit processor, this is the k that we are referring to. The Mux, its job is to take one of these source and send it to the output, that data item to the output. So the output is also k bit. And then I have these control signals, a select control S, which tells me which one of these sources to send to the output. And what we do is we encode it in a one hot fashion. So I have n wires because I have n sources. So if S0 is high, then A0, the k bits of A0 are going to be sent to the output. If S is I, then AI, source number I, its k bit will be sent to the output. So that's the logic's written out here. It's basically saying if Si, if the ith wire of S is 1, then B gets the value AI, where I is whichever source it is. Okay, the ith source. That's what I'm sending out. And this functionality, like I said, I mean, it's integral to multiplexers are in basically every digital system, because this ability to get the data from different places is needed again and again in many systems. Implementing it is straightforward. So for example, if I want to create a 4:1 multiplexer of 1 bit each, so n equal to 4 and k equal to 1, then this is the implementation. What is basically 4 AND gates and a OR gate. So A0, A1, A2, and A3 are 1-bit signals from 4 different sources. S0 says output should be the same as A0. S1 says output should be the same as A1, and so on and so forth. And we are guaranteed that exactly one of S0, S1, S2, and S3 will be high. So if S2 is high, then all the other 3 AND gates are going to have an output of 0. And this second from bottom gate, it would see S2 is 1, and so output of the AND gate would be A2. So A2 appears out here, and on the OR gate, 3 of the inputs would be 0, and 1 of them would be the same as the corresponding A input, and therefore that will appear out here. So you can kind of work out the logic that this acts as a 4:1 multiplexer. If I want to create a 2-bit version of this multiplexer, so 4 sources and 2 bits, then all I have to do is I have to make an extra copy of this, feed the second bits of A's to that, but the S's remain the same, right? Because when I say S2 is high, then I mean lower bit and upper bit of A2 map to the lower bit and upper bit of B. So if I want a 32-bit multiplexer, I make 32 copies of it. The different bit numbers of A1 will go to the different slices, different bit numbers of A2 will go to the different copy, but S1, S2, S1, S0 will go to all 32 of them, S1 will go to all 32 of them, and so on and so forth. So we just kind of make this replication. So Muxes are extremely useful. In fact, they are so useful that we need to implement them particularly efficiently, and many a times there are a large number of resources. Like I may have, just to give you an example, motherboard of your sort of tower type computers or kind of a biggish computer may have, I don't know, 8 memory DIMMs or 16 slots where you can put in memory, and there's going to be some multiplexer which is kind of going to take this data and feed it to the processor. So it's very common that I will have multiplexers with a large number of sources. N is very large, and if I were to implement it naively, then as shown out here, then I would need many OR gates, and I will need a huge many AND gates, and I'll need a huge OR gate. Instead, we begin to rely on, and this is one place where we begin to go into the physical implementation of the gate. In particular, imagine a gate. So the idea is the following: in electrical circuitry, if a wire has a voltage, and if I have another wire which has a different voltage, when I hook them together, bad things happen, right? I mean, it's like shorting hot wire on your power supply to the ground wire, or okay, so bad things will happen. Same thing in chips, okay? So what we would like to do is take these different sources and tie them together, but make sure I'm able to select just one of them. So to make that happen, we sort of create the special kind of electrical gate, which so I have an inverter out here, and I have this identity function, a buffer. Think of it, it's kind of like an inverter, but it doesn't invert, it just passes the signal through. And you see it has this special signal which is labeled E. It's called enable. And what enable does is the following: if enable is high, then the inverter behaves like an inverter. So you see, whenever enable is high, the X is not of A. But whenever enable is low, the output is disconnected. It's as if this inverter has been removed from the circuit. There is nothing driving this piece of wire, which means if I had 2 of these hooked up together, and if one was driving and the other was disconnected, it's okay. And we'll see how we can make a mux out of that. And likewise, this guy, this is just an identity function. So X is equal to A if E is high, but if E is low, then X is disconnected. That's what we see out here. These kind of circuits are called tri-state circuits, because they're called tri-state because the output can take 3 different values: 0, 1, or disconnected, and electrically disconnected. Okay. So, and it's often referred to as floating or high impedance or high Z or just simply Z. There are many different conventions kind of used. Now the reason it helps us is the following: I can make multiplexers using this. So I can take 4 inverters, which are tri-state inverters, and we connect their wire together. Normally, if they were regular inverters and we connect their wire together, bad things will happen, because some inverters will try to put out the voltage for 0, some may put out voltage for 1, and electrically bad things will happen. But here, what we do is we arrange that at any given time, exactly one of them is enabled and the other 3 are disabled. and then it will act like a multiplexer. So for example, if E0 is high and E1, E2, and E3 are low, then X is going to be equal to A0 invert in this case. Likewise, if E2 is high and the other three are enables are low, then X is going to be equal to A2 invert. So I have a multiplexing, I have a inverting multiplexer now. Okay, it's acting like a multiplexer, but it's also complementing the value as we go along. So let's see. Yeah, go ahead.
Wouldn't you have, so you would have to put in additional circuitry to ensure that only one was actually high, right?
Correct, but if they are one hot coded, as in a normal multiplexer, that's already there.
Okay, but
Right.
Within a multiplexer, wouldn't it have to? It would not make that assumption, and the circuitry would exist to put it through like a.
Fair point. So what you're saying is, if I had a normal multiplexer and if I violated that assumption, bad things will not happen. Whereas here, electrically, bad things will happen.
Right.
You are right, and therefore one has to be careful in a design like this. Yeah.
Okay.
Okay. It's kind of like saying, I don't know, I give you a piece of hardware, and if you feed it the wrong values, it will blow up or something like that. I mean, it's that kind of thing. Okay, so yeah, you have to just make sure it doesn't happen. Yeah. So floating means electrically disconnected. Okay, whereas invalid means that I connected. There are two or more gates driving that signal actively, and they happen to have different voltages. So like imagine I have one inverter which is outputting 0, another inverter which is outputting 1, and I electrically short their output. So now think about what would the voltage be. One guy is trying to drive it to 0 volt, the other is driving it to, let's say, 5 volt. I tie them together, current will flow from a power supply down to your ground, and that would be bad. Okay, so invalid means it is some voltage, but it's electrically bad. Okay, whereas floating means it's disconnected. Okay, so I think that, and then I also kind of talked about that how we can create multiplexers where the control input can, instead of being one hot, is binary encoded. Okay, and I guess to answer your question that you're asking, how do I make sure that that maybe for the tri-state type logic, it's better idea to take always binary encoded control and then do the generate enables yourself, and by do that by having additional circuitry. Okay, so and I can implement it by combining a Mux and a decoder. So it just okay. So just like decoder could be used for arbitrary logic functions, so can multiplexers be. And let me show how it can be done, because it's a very powerful way of implementing logic as well. So so the assertion I'm making is, if I give you a multiplexer, let's say I give you a 4:1 multiplexer, then I'm basically claiming that it can implement any function of 2 inputs each, of 2 input. And let's see how that might work. Or in this example, I'm giving you 8:1 multiplexer. It is a binary coded multiplexer, so it's taking 3 inputs. Okay, and now let's look at this control input SB. If SB is 0, 0, 0, then the my input numbers are labeled like this: 0, 1, 2 through 7 or 6. So think about when SB is 0, 0, 0, then this multiplexer will take the value on the 0th wire and send it to the output. And what I've done is I've tied the 0th wire to 0. So whenever SB is 0, 0, 0, so let's just, I have SB and I have output. Whenever SB is 0, 0, 0, then the value on the 0th source goes out there, which in our case is tied to 0. When SB is 0, 0, 1, then the value on the first wire, A1, goes to the output, so I get a 1, and so on and so forth. If the value was 1, 1, 1, then the value on the last wire, bottom wire, is going to go to the output, and my output would be 1. So whatever I have tied my inputs to really correspond to the output column of my truth table. And this is basically saying select a row of my truth table. Is that obvious to, or not obvious to anyone? Okay, I have as many inputs. I have, if my SB is n bits, then I will have 2 to the power n sources. And I'm basically saying that whatever binary value I have out here, take that input and send it to the output, and then we arrange that input to have just the right value. So by given a multiplexer with 2 to the power n sources, then it will have an n-bit control, because this is a binary select, not one hot coded there, and then I can implement any function of n inputs. So decoder can be used for arbitrary logic, but so can multiplexer be used for arbitrary logic. So quite useful. And in fact, what you would find is that there are these chips where they just put a lot of multiplexers, and then they put on these wires a fuse, which or kind of like a switch, using which you, for each input, you can either set it to 1 or 0. And then the idea is that you buy these chips from your software, from your computer, you configure each one of the inputs, and voila, you have your whatever function you want to implement. So, so essentially, it gives you these kind of software programmable hardware. Okay, hardware where you have these muxes, and then you have these switches at the inputs.
So would you need a decoder to convert the signal, the select signal?
No, so this one, when it says SB, it is already, internally there will be a decoder. That depends on how this multiplexer is implemented, but you're right that internally there will be a decoder which would be doing that. So multiplexers can therefore be viewed as arbitrary, as a flexible way of implementing an arbitrary logic. Go ahead.
When you have the hardware and you can program it on your computer, is that an FPGA?
Yes, that's an FPGA. So FPGA stands for Field Programmable Gate Array. So field programmable means I can do it on my desk or out in the field, as opposed to it having to be done in the factory. Okay. Now, of course, the problem with this thing is that if I needed, with this example was that I needed a 8-input multiplexer. Could I simplify it? Could I implement this thing using a 4-input multiplexer? Now the issue out here is that I'm only tying the inputs to zeros or ones. Maybe I can be a little bit creative. Some of my input bits I can feed here to the select, and some of my input bits I can feed to the sources, and then can have a more get away with a smaller multiplexer. So let's see how that can be done. So in this particular case, what we do is the following: that we send. So look at it this way: that the lower 2 bits of my input, which were going to SB0 and SB1, they take 4 possible values: 0, 0, 0, 1, 1, 0, 1, 1. And we still feed them into a control input, but of a 4:1 multiplexer now. The third bit, which was normally going to SB2, can take 2 different values. It can take the value 0 or it can take the value 1. Let's see if it takes the value 0. Well, if it takes the value 0, then this particular box corresponds to input being 0, 0, 0. And since we are doing the is prime function, this is 0. The second box out here, this corresponds to 1, 0, 1, which is the number 5, which is prime, so it's 1. Next one corresponds to 0, 1, 0, which is the number 2, which is prime. Final one corresponds to 0, 1, 1, which is the number 3, and therefore we have a high out here. The second possibility is that SB2 was 1. So the box out here is going to correspond to 0, 0, 0. Sorry, 1, 1, 0, 0, which is a number 4, which is not primed, so that's why we have a 0. Next one is corresponds to 1, 0. Did I mess up? Yeah, okay. So let me write. This corresponds to the number 0, this corresponds to the number 1, this corresponds to the number 2 and 3. Okay, so in our example, we are always considering 1 as part of its prime, so that's why we have 0, 1, 1, 1. This corresponds to 4, 5, 6, and 7. So, so what we have done is we have shown kind of the output as they would appear. Now, the issue out here is I only have a 4:1 mux. So in the 4:1 mux, I'm feeding this. So I cannot, unlike the previous example where we were tying the inputs to only zeros and ones, I cannot do that anymore. But I can potentially be kind of a little bit smart out here. If you look at, there were two cases. One case is when SB2 is 0, the other case is when SB2 is 1. And we try to come up with an equation which subsumes both, an equation out here which is in terms of SB2. So if you look at the first row, whether SB2 is 0 or SB2 is 1, the output is 0. And therefore, I will just put a 0 out there because in either case, the output is going to be 0. Next one, in either case, the output is 1. So I'm going to make that source number 1 to be 1. Third case is tricky. Third case says that if SB2 is 0, then output is 1. But if SB2 is 1, output is 0. So source number 2, I guess this was source 0, 1, and 2. Source number 2, I have a problem. I don't know whether to tie the wire to 0 or to 1. But you can tie it to invert of SB2. Okay, so that will do the trick for us. So not SB2, and final one is 1. So what that means is I have a circuit like this. 0, 1, not SB2, and 1. So now I can get away with a 4:1 mux, which is much cheaper, and I pay for it in one additional inverter. Okay, so I guess the idea is you want to use smaller multiplexers, but of course applying this strategy too much would begin to result in very complicated expressions out here, so you don't want to take it too far. So you want to just get the right balance. Okay, don't use, if you have n inputs to play with, don't use a 2 to the power n/1 multiplexer. Try to aim for something smaller with the goal that if you select input smartly, maybe you can have very simple expressions out here and get away with it. That's kind of the idea. Go ahead.
If we were to take like a basic implementation of the FPGA, how big would your muxes be?
In FPGAs, usually, so firstly, as the name implies, field programmable gate array. So they have a large number of these inverters. Each one of these multiplexers, usually these multiplexers would probably be 5, 6, maybe 7 inputs, no more than that. Okay. But obviously, it kind of depends upon specific chip models now. So building big multiplexers out of smaller multiplexers. So let's say you have a multiplexer with n inputs and I have another multiplexer with m inputs. Then I can create multiplexers with m times n inputs. What I can do is, so it's kind of like, let's say I only give you two to 1 multiplexers, and I actually needed a 4:1 multiplexer. What I can do is I can have one 2:1 multiplexer, and on each one of its input I can put another 2:1 multiplexer, and then overall I'll have a 4:1 multiplexer. So likewise, if I have n input and m input thing, I can kind of combine them together. Bottom line is, if I give you 2 input multiplexer, I can build any size multiplexer. All I need to do is to kind of just keep combining them repeatedly. So to give you an example, let's say I want, so this is what I mean. Let's see if I have a diagram already there. Yeah, here I am. Okay. So what is happening out here is I have a bunch of 4:1 multiplexers. So I take four 4:1 multiplexer. I take their output and feed them into another 4:1 multiplexer. And now I have a 16:1 multiplexer where the lower 2 bits of my control select one of these source multiplexers, and the upper bit selects upper 2 bits select this one. So I'm still taking 4 bits of control. So 2 out here, 2 out here, because it's 16:1. But I make it using 5 4:1 multiplexers, and I can take this thing to kind of ever larger size. So I can combine multiplexers in this particular way. Okay, so again, decoder, encoder, multiplexers. Now we move to kind of a more interesting logic, something called arbiter. So what does the English word arbiter mean? Huh?
Truth.
Truth? No. Arbiter doesn't mean truth. Anyone? Arbiter, arbitrator. It's actually many a times when you're silently clicking OK on all these licensing forms and all, you're agreeing to arbitration. Do you know what that means? Arbiter is like a judge who basically, so we're basically saying that, look, instead of going to the court of law, these companies make you sign things saying, in case of a dispute, we'll go to an arbiter who will basically listen to both sides and basically select who is right and who's wrong. Okay, so arbiter selects one person to be a winner, or more, one out of, I mean, in legal cases, 1 out of 2, but more generally 1 out of n. So I have n things, and I'm going to select a winner. And this situation happens a lot of time in computing devices also, that there are many things which are striving for attention from a resource. So for example, maybe at the same time, there are many different devices on my computer, all want access to the CPU. So somehow they need to get attention to the CPU. One of them has to be selected as a winner, saying, hey, you get the CPU. Or to take another example, let's say our Wi-Fi networks. All our computer devices and all, they're trying to talk to the same access point, but of course not all of them can send out data exactly at the same time. So there has to be some way that one of them at any given instant is selected as a winner, and it gets to use the spectrum to transmit. And then a little bit later, someone else is selected as a winner, they get to transmit, and so on and so forth. So there is an arbitration going on. It's done by hardware, done by software, some done by combination or two, but that's kind of where this stuff comes from. So arbiter basically is something which handles requests from multiple devices and selects a winner. Okay. So what is happening out or take another example. Yeah, I don't know if any of you watch Jeopardy, or take any other game where like simultaneously multiple people are trying to do something in Jeopardy. Multiple people attempt to answer, but one of them gets the chance to answer, right? We select a winner. So it's a box which has n inputs and it also has n outputs. But imagine, and so each wire corresponds to one of the players, one of the devices. And what we do is at any given point in time, we tell the devices, if you want the resource, make your wire 1. So what these guys do is, if they need the resource, if they want to play, they raise their corresponding wire. So if 3 devices want the resource, 3 of these wires would be high. But we are allowed to have only one winner. Okay, so one way of thinking about it is, there are these n wires, again 1 for each player, and on each wire there is a lamp saying you won, and we want only one of those lamps to light up. Okay, so if player number 3, 4, and 5 are playing, they raise their wire. We have to select one of them to be the winner, and that wire should be high. So that's kind of the concept. That at any given point in time, there could be multiple simultaneous requests, but among those who requested, I need to select one of them to be the winner. That's called arbiter. Now, of course, in this case, there has to be a policy. That is, if there are multiple things, which one do I select the winner? Well, could be any number of policy. One policy is maybe all things considered, I will pick as the winner the one who has not won for the longest time. Okay, or it could be that I give everyone an ID and I say whenever multiple people want attention, I'm going to take the one with the smallest ID. Unfair, but a perfectly fine policy. So in particular, what we want to do is the following. On this, so R and G stand for request and grant. Request is where players are requesting attention. Grant is one of the grant wires will be high saying, hey, player number I, you can proceed. You won. What we do, so what we are seeing out here is a vector of bits, n bits. And what we'll do is we'll find the first one bit in R. So we are going to start from one of the ends, okay, either the least significant or the most significant side. And the first one bit that we encounter, we would basically say that that person is the winner. So in particular, we say that GI is 1 if RI is 1. So ith player is the winner if ith player made a request, RI equal to 1, and none of the players with a smaller index made a request. So we start looking from player number 0, player number 1, 2, 3 through n minus 1, and we say player number 0, did you make a request? If so, you are the winner. If it didn't make a request, player number 1, did you make a request? If so, you are the winner. If not, we move to the next one all the way up. So that's all it is saying. It's basically saying ith player is a winner if it requested and none of the players earlier than I made a request. Clear what we're trying to do? Okay, so winning, one winner has to be selected. So the logic out here literally translates into kind of the equation that we had out here. We want to say ith player is a winner if it made a request and nothing previously made a request. Okay, so this in programming courses you might have seen this notion of like recursion. Anyone seen recursion? Right? I mean, you always kind of, or like when we do definition of factorial and whatnot, it's always like we take one case and express it in terms of a previous case. Same thing going on out here. So we're basically saying GI is high, ith player gets the grant if it requested and no one has yet requested. So I create the special signal coming in calling no one yet I minus 1, which basically says that player number 0 through I minus 1 have not made a request. And so if both these conditions are true, that ith player made a request and none of the previous players have made a request, then GI is given. And then of course the other thing we have to do is we need to supply a signal for the next stage. So I have to generate the signal called no one yet sub I, whose interpretation is none of the players from 0 through I have requested. So that, as you can see, translates into none of the players from 0 through I minus 1 requested, and I also has not requested, which is why we have a bubble out here. Okay, so a single stage basically it's boiling down to this, right? So this gate is corresponding to saying that ith device requested and 0 through I minus 1 have not. Right, so that's the interpretation of this signal. This signal is saying that, and then for me to be able to recurse, kind of make this work for the next bit, I also need to generate this signal, which is basically saying not 0 through I have not requested. Okay, none of them, none of the players from 0 through I have requested. So I make this kind of a logic. And then my arbiter, what do you think it will look like? Using this, can you make a big arbiter, complete arbiter, n-bit arbiter?
Going
Yeah, what do you want to keep doing down, keep doing? I mean, I give you this box. Let's say this is all I give to you. I give you a black box which does this function. It has 2 inputs and 2 outputs. Can you make an n-bit arbiter out of it?
So you would, I guess you kind of have to like use up one of the inputs, but you could and all of the or all of the outputs together and feed it into the next multiplexer.
I don't even have to do that. I think
Just chain them together.
just chain them together, right? Next stage, I repeat this logic, tie outgoing of this to the incoming one of that, and keep going like this. The only thing I have to worry about is what happens at the very beginning. You select it to put it to 0, no 1 1 yet, right? So this is what it looks like. This cluster out here, this is what I have on the previous slide, and I've just repeated that logic, right? And at the very top out here, what we are basically saying is that no one yet has requested. So actually it should be a 1 because we have a logic other way around. So we are basically saying this should be 1 because no one yet requested. And then each stage is basically deciding on the grant and telling whether to the next stage whether anyone has requested thus far or not. Okay. Is there anything bad about this circuit that you see?
There's some settling behavior at the beginning when, like, depending on the propagation delay, then your outputs would like roll to the final state kind of.
Okay. So, but I was looking for something even. You're right.
I have a question. The first one, you decide if you put it like 1 or 0.
Yeah, you mean at the very top?
Yeah.
Yeah. So we have to go by the plain English meaning out here. The meaning is no one yet has requested. So if we are on the very first one, no one yet has requested, therefore it is 1. Okay, and this symbol means that things are connected to a high value. So this means electrically it's kind of like I'm connecting to something else, and this usually means 0 value. This means 1. Okay, so I'm tying it to the power supply versus tying it to the ground. Okay, so this is basically saying 1. And okay, so you were describing more complicated behavior. All I was looking for, look at the worst case delay out here. For G3 to settle, I have to go through all these signals out here. Okay, so if I'm arbitrating between 100 devices, I will have to go through 100 gates out here. Okay, but that's the nature of this design. The issue that you are bringing out is the following: that even if all my inputs arrived at the same time, as the signal propagates down, if someone were to be watching one of these signals, the signal here may flip multiple times up and down, a little bit like our hazard situation that we had seen in an earlier lecture. Okay, so it may take some time before the outputs are all stable. Okay, so this is an arbiter, and again, arbiters are also extremely useful in computing devices because again there are a lot of these shared resources. There might be a network card or a radio or a bus in your computer, which may be multiple entities may be competing for, and therefore this kind of arbitration logic is present. Okay, so this is a 4-bit arbiter. This is also a 4-bit arbiter. Here what I have done is I've taken kind of this, remember this 4-bit arbiter, I can write a truth table for it, right? I mean, it's just a mathematical function. It's a function which takes 4 inputs and gives 4 outputs. So I can write a mathematical function and then I can reduce it to an equation, and you'll see that I can implement it like this. Now here, the advantage is it's fast because any output goes through only 1 gate. So from input to output, there is 1 gate of delay. Not quite. These gates are growing up. Like this gate, the first gate had 2 inputs, second gate has 3 inputs, third gate has 4 inputs. If I have 100 sources, then the final gate is going to have 99 inputs. So it's going to be kind of a monster AND gate and not very good. It will have huge delays. Whereas here, even though my gates are simple, I have 100 stages of them. Okay, so which one wins out, which one not, kind of depends. You may end up with like some really truly huge transistors and circuits out here. This circuit is probably going to be much lower in area, but it's going to be slower. Okay, whereas this circuit is going to be larger in area, but it's going to be faster. So large but fast, and this one small but slow. Okay, and what we are referring to is that as you look at the signal goes through this long delay. So in any given circuit, there are always these paths from input to output, and the delay through them, there could be many. So here, for example, I have 4 inputs, 4 outputs. There are many different paths, like for example, from R0, there is R0 to G0, there is R0 to G1, R0 to G2, R0 to G3. In any given circuit, there is going to be some paths which are longer, some which are smaller. The longest path, the one which has the worst delay, is called the critical path. So longest delay path is called critical path. It's called critical because it dictates how fast my circuit is going to run. Right? After doing one operation, when can I do the next operation on that circuit? So 4-bit arbiters. And the same concept you can apply. So which one is better? We kind of discussed the trade-offs. Okay, these slides are just going over. So there's a long delay out here, whereas the delay with that particular circuitry is shorter. Okay, so arbiters, extremely useful. Final module in this sequence of things before we move to the next type of modules is something called priority encoder. So the priority encoder does the following. I have an n-bit signal. I have an n-bit signal. I have an m-bit output signal. So A and B are signal. A is n-bit, B is m-bits. B indicates the position of the first bit, 1 bit in A. So think of it like in an arbiter, the output was 1 hot coded. Output wire number I was high if the ith input wire was high and nothing lower than I had made a request. Here what we are doing is we are basically saying that B will have the numeric value I if AI is high and A0 through A-1 are low. So instead of 1 hot coding, I have a binary coding out here. Right? It's basic. So firstly, what do you think would be M in terms of N? What's the relationship? I'm saying B is M bit, A is N bit. What is M in terms of N? Log base 2n. Okay, because it's a binary encoding. Using the modules we have seen thus far, how can you implement a priority encoder? So arbiter was telling me, arbiter was raising the ith wire if the ith input was the one which was a winner. Here I'm saying that B should have the value I if ith input is a winner. Arbiter and a decoder, right? So that's what do the trick. Sorry, arbiter and an encoder, not a decoder. We have to go smaller. Okay, so that will do the trick out here. So the thing that I want takeaway is that I can create richer functionality by combining these modules together. Okay, and that's something that one has to kind of remember. So let's take an example. Let's say I want to create an equality comparator. So in programming languages, we all have this operator equal equal, right? When I say x equal equal y, it means x and y have the same value. Or another way of saying is the bit representation of x and the bit representation of y are exactly identical. So I want to create a circuit out here where I'm taking two n bits input, a and b, and a single bit output EQ. EQ is high if all the corresponding bits of a and b are equal. So like a0 is equal to b0, a1 is equal to a1 is equal to b1, a2 equal to b2, and so on and so forth. So it's equal equals EQ equals 1 if and only if a sub I is equal to b sub I for all values of I. There's a slight typo out here. This should be n minus 1. Okay. So any thoughts? How can you implement this?
So you could do A and B, and then the second set would be not A and not B, and then take the OR of the result of those both.
What is that called? XOR. Okay, so I can have XOR for each bit. So I can have n 2 input XOR gates. Okay, I take their output. What do I do with them? Huh? And them together, right? Each one of them. Sorry, we are looking at equality, so you'll use XNOR. So you'll take n XNOR gates and then AND them together. Okay. That everyone see. So XOR function is XNOR function is an equality function. Is a single bit equality function. Those of you are attempting problem number 8, you can kind of reason about some of those properties. So this is what it would look like. XNOR EQ3 is saying bit number 3 is equal. EQ2 is saying bits at position 2 are equal, and EQ1, EQ0, and then we're basically saying 2 are equal if all the bits are equal. So the trick out here is, a lot of digital design, much like software, boils down to you would have some sort of a plain English description of the functionality that is needed. And then you need to create the corresponding logic from it. And these things are too complicated to do the Karnaugh map based approach. Usually there are way too many inputs. So the trick is that you have to implement them using these kind of modules. Like if you look at this example, it has 8 inputs, right? So you could certainly define EQ as with a 256 entry truth table or an 8-dimensional Karnaugh map. You will not get very far. In fact, just feeding these things would be laborious. So, so this is where this divide and conquer strategy, we know that some of these other modules do certain functionality, and so this is nothing but like an algorithm, right? I mean, we are basically thinking of our XNOR gate as kind of a subroutine, which is a bit level checker, and then we are ANDing them together to kind of create my bigger, more complicated subroutine. So if you start thinking of digital logic a bit like software, then really all that is happening is your algorithm, instead of being in code, is in gates. But it's kind of analogy kind of is like that. So let's take another one, magnitude comparator. So what I want is, I have a module which takes 2 n-bit inputs, gives out an output called GT, and we say GT is 1 if the value represented by the bits at A is greater than the value represented by B, strictly greater than. Okay, so how do you think you can do that? This is a trickier example, so let's walk through it. Equality was simple, but greater than, we have not seen it, but you'll see that it works a little bit like arbiter. Okay, so how do we compare two numbers? So let's say I give you these two numbers. These are 6-bit numbers, 001110 and 001011. Okay, so let's say I give you two 6-bit numbers. what algorithm would you use to compare them?
At the first point of difference.
Huh?
At the first point of difference, like you compare each element.
So which direction would you start from?
The left.
Most significant, right? So so I'll start from, so one approach is start from the left. You can actually also do it from the right, but let's start from the left. So in this case, we'll say bits number at position 5, are they equal or not? Well, both of them are equal, so I try the next one. 4, they are equal, again I move on. 3, they are equal, I move on. At 2, first A has 1 and B has 0, so A1, A is greater. Right? I mean, this is exact analogy of what we do with decimal numbers. We kind of scan from the left and until we hit the point of difference and then pick the winner out of it. You could also do it from the right hand side actually also. So let's see how these things work out. Okay. Let's look at this circuit. So it's a complicated looking thing out here. So what's happening out here is the following. I have AI and BI. I generate, so I'm looking at bit number I, and I generate 2 intermediate variables out of it. I generate a variable called EQI, which basically says these 2 bits are equal. And I generate a variable called GTI, which says AI is greater than BI. Okay, so equal, we already saw. GTI would be high whenever AI is 1 and BI is 0. And therefore, we have this AND gate with an inverter at one of the inputs. Okay, so I have these 2 intermediate variables. AI equal to BI and AI greater than BI. Let's introduce this third variable, which we call as GTBI. And it is let's look at this this signal, which is coming from lower bits. And what we do is we indicate that GTBI equal to 1 means that for these lower bits, if I just look at those bits, bits number 0 through I minus 1, then input A is greater than B. Okay, so to give you an example, if I were to, let's say, for example, just look at these lower 3 bits, then looking at this, we can say A is greater than B. So at this stage, when I'm going from here to here, GTB3 will be equal to 1. Okay, because A is, so that's how we are defining the stuff thus far. And then let's see what this logic does. We are basically saying that GTBI I plus 1 means that from bit number 0 through the current bit, A is greater than B. Now, when can that happen? It can happen either because right in this bit, AI is greater than BI. Right? Because if AI is 1 and BI is 0, then none of the lower bits matter. Is that obvious, right? I mean, if I'm looking at the current bit position and if A is greater than B, then the lower bits do not matter. So that's one case. The other case is that these 2 bits are equal, but the lower bits tell me that A is greater than B. So that's what we are seeing out here. This AND gate basically says at the ith position A and B are equal, but the lower bits tell me that A is greater than B. So what this guy is saying is an ORing of the 2. So we are basically saying either at the current bit A wins, or at the current bit A and B are tied, but on the lower bits A won, A was higher. And those 2 cases we combine, and that's how we get this. And we keep feeding it up the chain, and at the end we are going to get A greater than B. The final GTB will tell me whether A is greater than B or not. So unlike the previous solution where we were starting from the left, in this case we are starting from the right. We are starting from the least significant bit side.
When starting from the left, theoretically, mean that you could either do it faster or you could make it faster theoretically?
I would have you guys try it out. Yeah, it's going to be different. Now, again, similar kind of this iterative or whatever recursive structure is going to be there. So breaking up the problem like this, I mean, again, if you look at it, I mean, this is not all that dissimilar from when you first learned about recursion or iteration, right? I mean, that's the way we are kind of forming these things. Same structure except in hardware it's going on. There was someone raising the hand out here.
Sorry,
yeah.
So how's GTBI the next one if it's AI and BI then? Isn't it?
So next stage we'll see AI plus 1 and BI plus 1. We are going to repeat the same thing. We are going to say, so if let's say GTBI plus 1 is high, that means bits I through 0 tell me that A is greater than B. Now let's test bit I plus 1. So I think my next slide should have a slide. So it kind of is going to look like this. So I'm going to start out with bit 0, then go to bit 1, bit 2, bit 3. If it's a 4-bit comparison, the final output is going to be GT. Okay, and here at the very bottom, again I have to initialize. So I have to say what does GT0 tells me? Well, what does GTB 0 tell me? That is A greater than B before I started? Well, no, because there is nothing before that. So A is not greater than B. So we start with a 0. Okay, and we kind of cascade like this. And then the final thing out here, which is GTB4, is basically saying that from bits number 0 through 3 is A greater than B. So that's the interpretation that we are saying. So this is the GT sign. This circuit suffers from exactly the same issue that we previously talked about, which is long delay, right? I mean, we will have this signal will kind of go through all these gates and come up out there. Like the worst, what can you tell me for what values of A and B would this circuit face the worst case delay? Huh? Okay, or they just differ in the last bit. So 0, 0, 0, 1, 0, 0, 0, 0. Okay, so then the effect. So if the upper 3 bits are identical and the lower bits is the one which is making the decision, then the signal will have to propagate all the way through. Questions on this? Yeah.
But for all numbers, wouldn't it still have to traverse the whole thing? For regardless of which.
Yeah, worst case delay you still have to traverse.
But I'm saying for all cases, wouldn't you have to? Still...
Yeah.
Oh, okay. I guess look at it this way. If I presented one set of numbers and then I changed it, how long would it be before I see a new output? Okay. So if I changed 1, 0, 0, so let's say the two numbers were 0, 0, 0, 0 and 0, 1, 1, 1. Let's say things are stable. I changed the second number to 1, 1, 1, 1. Sorry, I changed the first number to 1, 0, 0, 0. So the output change would be quick. The other extreme would be slow.
You would have to go through the entire thing to see if it had changed, right? Like, even if you change your lower bit, like your upper section might still have changed back lower, so you'd have to go through the whole system in order to
Yeah, I mean, the point both of you are making is the following. I don't know what the values are, so I have to be prepared for the worst case in these designs. Right. Okay, so in that sense, hardware is a bit unlike software. In the software, when I call the function with some arguments, when it returns, if it was quick, it will return quickly. If it took a long time, it will take a long time, but I have an explicit thing which says, now the function is done. In the hardware, I do not have anything at the output where the hardware says, hey, I'm done. Okay, you have to be prepared, always be prepared that the worst case delay that the hardware can take and budget for that time.
But if you check from the upper side, like you could always have your changes propagate faster, right? Like,
oh, so you're arriving at that if we were to follow the original algorithm that I can always do it faster? Not really, because in the worst case, if the change is happening at the least significant bit size, then you'll have to wait all the way there still.
For this one, you would have to go through the whole thing every single time, whereas that one you could find it theoretically not worst case.
No, that's not true. I mean, again, in this particular case, if only the upper bits were changing, then I don't have to traverse. My answer will come back quickly. If the hardware had a magical way of telling me I'm done, right? Then I can have a data dependent, and there are such hardware also. There's a question in the back. Yeah.
So is the most significant bit, I guess, compared first?
No, in this case, most significant bit has been compared last. Whereas the other algorithm which was suggested was most significant bit was compared first, which is a more intuitive thing, right? I mean, when we compare numbers, we start from the most significant bit.
When I said first, I mean it's
Huh?
When I said first, I mean it's
That is correct. I mean, so what's going to happen is that these the stage with the XNOR and this funky AND gate, they are all computing in parallel, right? Because when the signals arrive, all these 4 stages are going to be in parallel, but then the signal starts propagating out here. So the least delay is indeed from A3, B3 to GT, and the longest delay is from this guy to GT. Yeah, the reason you have to still wait for the worst case is because hardware cannot tell you I'm done. Okay, so you have to be prepared for the worst case.
So, but if you actually did want to build a circuit like this that does this, then would you not want to buffer the output and have that buffer reflect the output only after you have some guarantee that the propagation is finished?
Yes, and we'll see that kind of stuff later in the course when we go to sequential. So you put, remember way early on in module number 2, I had talked about this register, which upon a clock kind of remembers a value. So what typically you would do is you'll put a register out there and you're going to clock it when you know that GT has settled. Okay. So that's what, but we'll see that kind of later. Yeah. More questions? Yeah.
How would you implement a system that would actually know that it's settled, or would you say like just calculate for worst case and then plot it then?
Most designs are done where you just figure out what the worst case delay is, add some additional margin to it because the delay depends upon temperature and stuff like that, and then design for that. But there are circuit styles where the circuit can tell you, hey, I'm done. Okay, but they come at a cost. They usually take twice the number of transistors or something like that, so you kind of lose there. Okay. But there are these kind of, there are ways of designing those circuits too. More questions? Okay, these are sort of somewhat tricky designs. So just be just when you go home, kind of spend some time looking at it. Okay, so just to sort of complete the story. So this is the other design, which in this case we want to start from the top. So what we now have is again kind of the initial circuit is, this part of the circuit is the same. So I generate EQI and GTI. And now we need 2 lines going down. One line says that the bits which are to the left of I tell me that A is equal to B. And the other line GTAI means the bits to the left of I tell me A is greater than B. And then I'm going to keep generating this signal the same way out here. So EQ, so to the next lower bit, I'm going to say that A is equal to B thus far if it was equal up to the previous stage and the current stage also says equal, right? That is, all the previous bits are equal. So that's sort of this equality. A is greater than B thus far if either A was greater thus far, the more significant bits tell me, or more significant bits told me that they were equal, and the current bit tells me that it is greater. Right? And that's what will go down. Now, can you see the disadvantage of this approach? Let's go back here. Let's go back here. More gates, because I have 2 signals propagating now. So that's an issue, obviously. But otherwise, kind of the design looks the same, except working in the reverse. I'm flowing from top down, and I have to initialize equality to 1. So things before the most significant bit tell me that A and B are equal and A is not greater than B. Okay, so 1 and 0. Putting things together. So again, remember I was telling that digital design is really about I give you an English spec and you have to design these things. So let's say I tell you design maximum. Okay, so I want you to, I'm giving you two numbers, n-bit numbers, and the output has to be an n-bit number, which is the higher of the two. So how would you do it in software? So let's say there was no max function available in your library. Okay, I give you A and B, or writing the max function. So
Conditionals.
yeah, so you say if A greater than B, then return A, otherwise return B. Okay, and I guess in case of tie, it doesn't really matter, right? So I do a comparison, and I'm doing a selection, right? When I'm saying if, else, I'm really doing a selection. In one case, I'm selecting one, in other case, I'm selecting the other. I map that to hardware. That's what it's going to look like. I have a magnitude comparator, which we just built. So I feed A and B to it. This tells me whether A is greater than B or not. And then I use a multiplexer. If A is greater than B, then let me see, have I done it correctly? Yeah, if A is greater than B, so I select the one input, so A goes to output, otherwise B goes to the output. Okay, so the mux part is corresponding to the if then else, and the comparator part is obviously corresponding to the greater than sign. Okay, and you can literally kind of take more complicated stuff and start implementing things like this. I mean, you can want to do average, you can do average. You can how would you take an average of two numbers if I were to not give you a division divider? I gave you an adder, but I didn't give you a I forgot to give you a divider. So I'm giving you two numbers, A and B, two binary numbers. Let's say they are both positive. Okay, A and B. I gave you an adder. I gave you an n-bit adder. I forgot to give you a divider. I want you to find the average. How would you do it? Shift. Shift which way? Shift right. Shift right. Shifting a number right is divide by 2. Ignoring the fractional parts. Just like in decimal numbers, divide by 10 means kind of dropping the 10, kind of shifting the digits to the right. Same story out there. We'll see more and more of this this part, but what I would like you to get into is thinking about that the digital logic is a way for you to express your algorithm. Really, that's what's happening out here. Okay, the problem statement gives you a design task, and you have these building blocks. That's your subroutine library, your API, your SDK, whatever, and you are going to be assembling thing, except that instead of writing code, you are writing gates or whatever, writing hardware. Okay, but really expressing an algorithm in hardware. It's just a different medium for writing stuff in. Okay, so there are some other tremendously useful types of combinational logic modules. We have seen earlier that Mux can be used to implement anything. Decoder can be used to implement arbitrary thing. There's a very powerful thing called ROM, read-only memory. Read-only memory is just a memory. So what? So computer memory, what does it do? Computer memory stores data. Whenever we need to fetch the data, we provided the address at which the data is stored, and the memory returns me the content of that address. So like for example, when you hear that this is a, I don't know, 32 gigabyte memory, well, that means that I have conceptually it's like a table with 32 gig slots. Their addresses go from 0, 1, 2, 3 through 32 gig. And then I give it an address. I say I'm interested in the value in slot number 100. So the memory takes that 100, the address, and then goes and looks in the slot there and returns me the value. When I say a memory is 32-bit memory, what that means is that the value in each slot is a 32-bit number. So there are two things going on. There is a number of addresses so number of slots that decide how many bits I need for the address. So for 32 gig, I would need how many? Should be good at binary numbers. So how many bits do I need for 32 gig of something? So remember, 32 bit, 4 gig. So 32 gig is going to be an additional 8, so 3 bits more, so 35 bits. Okay. Some common things to remember: 1K is 1024. Okay, so that's 10 bits. 1 meg is 1000 times 1000, 20 bits. 1 gig is 30 bit. 4 gig is 32 bit, and so on and so forth. Okay, so it's good to become conversant with that. Okay, so anyway, going back to our memory story. So memory is nothing but a bunch of locations which are addressable. Each has an address, and I give the memory the address, and it goes and looks into that location, and whatever data value is there, it returns that data value. So a memory takes an n-bit address. So if it has n-bit address, how many locations would it have? 2 to the power n, right? Because I can express n different 2 to the power n different slots. It will go into that location and then return me the value which is there. All locations are equal in size, so it's returning me a b-bit value. Okay. Read-only memory means I cannot write to it. All the locations have a fixed content. They're fixed at manufacturing time or fixed with some process, but after that I cannot write to it. So in software, oftentimes you have these things called lookup table. Like, I just create a fixed array. This is a fixed array in which I can index, and it will return me whatever is in that location. Okay, so in programming languages, this would be called an array which is constant. So it's a constant array where each where I have 2 to the power n minus 1 location. Sorry, 2 to the power n locations in the array, and each location is a b-bit number. So that's ROM. Now, what my claim is that using this, I can implement any n input m output function. Right? An n input m output function takes an n bit input, produces an m bit output. So let's say I give you an arbitrary n bit m input m output function. Can anyone suggest how might I use the ROM to do that? Okay, I see the same people raising the 4 people raising the hand. Anyone else? Come on, guys. Take a shot at this. So I'm giving you this table. You can store anything in the table.
You just store the answers.
Exactly, you store the answers, right? For if A is 0, if I'm supposed to return some number, I store that in the location number 0. If A is 100, whatever answer I want for 100, I store it in the 100th location, right? It's just a lookup table. I am looking up the answer. Okay, so it's cheating, but ROMs are very effective. Okay, if I give you a ROM, I can implement any function using that, right? It's just a gigantic array in which I'm just storing I'm pre-computing and storing my answers. So ROMs are extremely useful. In fact, they are so practically ROMs. So of course there are disadvantages also, right? The one other disadvantage is if certain input patterns I don't care about, I still need a location for them out here. Okay, generally speaking, ROMs will still have the location. Also, depending upon how these ROMs are designed, they could be slow and inefficient also. But actually, depending upon how they are designed, they can also be very compact because these designs are very regular. If you have ever seen a photo of a silicon chip, anyone seen ever like photos of silicon chips? Okay, you would see that usually there's some parts of the chip which are like jumbled up. Okay, and there's some part of the chip which are very regular. Okay, they're kind of almost beautifully Manhattan type grid. Usually memories correspond to things which are these beautiful looking Manhattan type grid. Your other logic corresponds to kind of this jumble of wires and all. Okay, so just Google for a die photo and you would see what I'm talking about. Usually memories kind of do that. Processors have memories in them. And then there are also memories externally. So you would see later in courses there is sort of memory which is very fast and which is on the same chip as the processor, and then there are large amounts of slower memory which are on our circuit boards and all. Okay, so they are sitting farther away. So ROMs can be used to implement store data, store fixed type data. I can store my programs in it. Like for example, have you ever heard, I don't know, any of you ever kind of go into like customizing your Android phone and all? Have you heard the term like custom ROMs? Anyone? I see you shaking your head. Okay, so that's because our phones and all have this kind of fixed piece of very low level software, okay, which drives the radio, the low level operating system and all, stored in ROM. Okay, now these ROMs are not, nowadays no one uses truly read-only memory. Truly read-only memory would mean you can never write to it again. But so it's better to call them as very hard to write to memory. Okay, I mean they are sort of not meant for user to write, but using either special tools or special software, you can write to them. How can we implement a ROM? Well, so one way we can implement a ROM is using modules that we have seen thus far. Let's see how are we doing in time. We have 3 minutes, so this is the last slide. So what I can do is I can take my address bits, I can create a decoder. The decoder will, remember a decoder does takes a binary number and produces a one hot coded output. So it tells me which slot I want to access. So exactly one of these wires is going to have a high value. So it's basically saying, so if A had the value I, then the ith wire would have a high value, and it's kind of basically saying unlock the ith location. In our case, we are going to use our friend the tri-state buffers. So we are going to say enable the ith tri-state buffer. And the input to that tri-state buffer is the value that I'm interested in. If I need 32-bit, I'm going to have 32 of these in parallel. Okay. In this case, I have B, so I have B of these in parallel. So the data sits out here. This data could be put out there in many different technological ways, but somehow it got there. And then when I'm reading it, that's all I'm doing. I'm going through this decoder, I'm activating the right tri-state buffer. So if you think about it, this is really a gigantic multiplexer, right? I'm basically multiplexing the data value from different locations into a single output and then selecting the right slot. That's what's going on. So our decoder and multiplexer are helping us create this ROM. Now, the main thing about ROMs and these kind of memories is they are very regular in structure, so people can design them very carefully and make them very compact, okay, as opposed to kind of doing things kind of the normal gate approach. So you'll often find them being used. You can implement very large ROMs also. So for example, what I can also do is, so I can take some address bits and select which, so I kind of break up the decoding. So what I do is, instead of having a single line of tri-state buffers, single line of locations, I make an array of locations, as 2D location. Some address bits tell me which row my data lies in, and then I use a multiplexer to select which column I should get the data from. So it's as if I'm using, so let's say, so in this particular case, I have 6 bits out here and I have 2 bits out here. 6 bits decide which one of the 64 rows I'm going to select, and all those tri-state buffers will be activated, and these 2 bits decide which one of these 4 columns I get the data from, and I dump it in the output. And the reason out here is speed and size. Basically, this kind of approach results in a memory which is kind of very long and thin, whereas this kind of approach results in a memory which is kind of more better aspect ratio, so you can put it on silicon much more nicely. So these circuits out here, these tri-state buffers, can actually be implemented with a single transistor. So they can be implemented very efficiently. I mean, basically, it's the most efficient thing that you can ever imagine, and therefore these memories can be implemented, large memories, and sort of small amount of silicon. So that's the benefit. So let's stop out here. We'll meet again on Wednesday.